move on now to the next lightning talk.
Hello everyone, I hope you're all enjoying the conference so far. My name is Luisa and I'm a PhD student at Maynooth University in Ireland. And today I'll present to you a small project that I've been doing under the supervision of Professor Peter Mooney around OpenStreetMap data quality when it comes to wind and solar energy infrastructures. As this presentation is pre-recorded, I won't be able to engage with you in real time, but I hope you still find it interesting, and please don't hesitate to contact me afterwards if you have any question or would like to provide some feedback. So let's get started. Our project focuses on OpenStreetMap power tag, and in particular, we're interested in generator and plant of wind and solar source. OpenStreetMap has an incredibly active community, and in the past few years, we've seen an incredible growth of the mapping effort around these tags. And in the slides, I've also included a link where you can explore how those efforts have evolved over time. Our main goal here is to understand what are the most common mapping errors concerning both geometries and tags, and study accuracy and completeness of OpenStreetMap representation of wind and solar farms. On a second moment, we would also like to integrate CORINE Land cover dataset to study the geographical distribution of these sites across different land types and evaluate potential implications. As case studies, we will focus on Ireland and Belgium. Here, I present to you a comparison of the tags that we used. If you look at the number of objects mapped for each tag, you will immediately understand the magnitude of the mapping effort globally. If you now shift your attention on the maps below, you will see how lots of these mapping efforts are focused around Europe, and this also justifies our choice of 2 European countries as case studies. As a first step, we aim at differentiating between individual installations and larger farms. To do so, we apply a point in polygon search on solar and wind nodes with intersecting areas of the same energy types. This approach allows us to identify some mapping errors, such as turbines mapped as circular areas instead of as nodes. But it also allows us to ask ourselves some geometric questions, such as what are the meaning of areas without nodes, and why are there so many nodes not assigned to any area? This last question is particularly significant when it comes to wind energy. And indeed, over 91% of turbines in Belgium and over 87% of turbines in Ireland are not assigned to any area. This particularly means that those turbines are not linked together by any area or relation and therefore are not included into larger farms. And this identifies a completeness issues in OpenStreetMap data. We would like to address this issue by using spatial clustering. In particular, we employ dbScan, which stands for density-based spatial clustering of application with noise. The most important parameter of this algorithm is the maximum distance between 2 turbines in order for them to be assigned to the same farm. We set this distance as 5 times the rotor diameter for onshore wind turbines. We observe how OpenStreetMap actually has a specific tag used to report the value of the diameter, of the rotor diameter. However, we also notice how this tag is often missing, and therefore we employ a standard diameter value of 130 meters for all turbines. On the slides, I've also included a table and a reference where you can find additional information on how to set the most appropriate value for the rotor diameter. After applying this algorithm, we can compare our clustering results with existing OpenStreetMap areas and relations. In doing so, we are able to identify unmapped farms, but also to extend existing OpenStreetMap linkages to previously unassigned nodes. At this stage, we can shift our attention to solar infrastructures, and in particular, we can focus on solar plants and solar generators. We notice how all solar objects are represented as areas. And we also know, according to OpenStreetMap guidelines, that solar farms should be mapped as plants. However, in practice, we notice deviation from these standards, and therefore, we decide to account for also solar generators. In particular, we apply an area-in-area search on solar generator, and we decide that if a solar generator encompasses multiple other solar generators, then it may denote a farm and therefore represent a tagging error, where a plant was wrongly mapped as a generator. This approach actually allows us to identify some tagging mistakes in Belgium and include those farms, correct the tagging, and include those farms in our final solar dataset. At this stage, we have 2 complete datasets of wind and solar farms for both Ireland, and Belgium. And we would like to understand the geographical distribution across different land types using CORINE land cover dataset. To do so, we apply a 1,000-meter buffer around those sites and evaluate the intersecting land types. Let's start by focusing on wind farms. Here you can see how a lot of wind farms in Ireland are located in close proximity of pastures and other natural areas such as scrubs and forests. While in Belgium, a lot of wind farms are in close proximity of agricultural areas, urban fabric, and arable land. Something that may be interesting to notice in Ireland is the proximity of wind farms with inland wetlands. And this is interesting because most of inland wetlands in Ireland are peat bogs. And peat bogs are a really fragile ecosystem that serve as a natural carbon storage. And therefore, the presence of this infrastructure near those lands need to be monitored very carefully in order to prevent possible negative impacts on the environment. Here, I present to you a map of Ireland colored according to land type, where peat bogs are colored in purple. On top of this map, I also represented the 1,000-meter buffer around wind farms. On the right corner of this slide, you can observe a zoom in a particular area where peat bogs and wind farms coexist. This is an example of a situation that needs to be monitored in order to prevent negative impacts. At this stage, we can repeat a similar analysis for solar farms. When it comes to solar energy, we notice how pastures are still very relevant in Ireland, but we also should consider that pastures cover over 50% of the Irish territory. After that, very relevant in Ireland are also arable land and urban fabric. Shifting our attention to Belgium, we observe how the most common land cover are urban fabric, agricultural land, and forests. Something that may be interesting to observe in Belgium is the coexistence of agricultural areas and solar farms. This is interesting because it may create agrivoltaics opportunities that have several potential positive impacts, such as improved crop yielding, decreased water usage, and enhanced soil moisture retention. Here, I present to you a map similar to the one that we saw before, but focusing on solar infrastructures and solar farms in Belgium. On the zoom area, you can see how, despite the highly fragmented nature of the territory, some solar farms are actually located in close proximity or on top of heterogeneous agricultural areas, represented here in light purple. And therefore, it may give rise to the opportunities that we mentioned before concerning agrivoltaics. To conclude, we demonstrate how to use spatial methodologies to enhance quality and completeness of OpenStreetMap data, and we believe that those methodologies can actually make OpenStreetMap a key source for renewable energy infrastructure data. Moving forward, we would like to validate our approach on a larger set of countries and include additional internal and external completeness and quality evaluations. Moreover, it will also be interesting to explore other infrastructure-related tags, such as operator, installation date, and generator output values. This makes the end of my presentation. I hope you enjoy it, and I would like to thank you for the attention. Once again, if you have any question, please don't hesitate to contact me. My email is on the slides. And you can also find a link to the GitHub repository where all the code for this project is stored. Thank you again for the attention, and I hope you enjoy the rest of the conference.
Okay, thank you to our two lightning talk presenters. And we're lagging on time, so we can have a round of applause for them. Yeah? Even if we're lagging on time, we can still be polite.